A wire of length 5 meter. Number 4. Of uniform circular cross section of diameter. So let's bring all these things out. Number 4. It has length 5 meter. Diameter 2 millimeter, which is 2 times 10 raised to the power minus 3 meter. Extension, that is x 1.5 millimeter, that is times 10 raised to the power minus 3 meter. Tension, force 100 Newton. Okay, so they now said calculate the energy E or U stored. So the energy stored in a wire is sent as work done per unit volume. I've said it before. Sent as work done F over S, unit volume E L, that is meter square times meter, meter cube for volume. So everything here is stress. Half work done per unit volume, half stress times strain. S over L is strain. So if I know this, I can now substitute. So this is something as saying R here will be the same as D over 2. 2 times 10 raised to the power minus 3 over 2, which is the same as 0.002 over 2. Then x is equals to 1. Okay, I've written that one. So to get the strain, strain will be equals to extension over length, and the extension is this, length is this, so 1.5 times 10 raised to the power minus 3 all over length, which is 5. So strain is equals to 0.0003. Strain has no dimension, just like this. Why the stress will simply be, remember we've gotten that the formula we use when we are doing work done for a wire, not for a string or spring, for a wire is simply energy there is simply work done per unit volume. I've written it. That is half work done per unit volume, or you say half stress times strain. So to get stress now will be force over area. So force given to us is 100 over area. Did not give us, but we know it's pi r square, or pi d over 2 r square. Then the d I'm given. By the time you divide this thing into 2, you get 0.001. That is for meter. The radius r. So if I put it there, I'm going to be having r here. Converting, that is, I converted the diameter. So stress will simply be equals to 100 over pi is 3.1429 times 0.001 square pi r square. So this is going to be the same thing as saying this one will give me 1 times 10 raised to the power minus 6. If you do the math very well, you get 3.142 times 10 raised to the power minus 6, because 17 times 1 is that thing. So by the time you now check it, stress will be equals to 100 over 3.142 times 10 raised to the power minus 6, which will give you 3.1826861.87. So you're not having points, but rather 3, 1, and you okay. So energy now will be half stress times 3. Should I think your handwriting is finer than my own? I'm rushing, that's why. I calm down to write. Who born you? Who goes you? So if you write this way, 31826 861.87, then times the string that we got 0.0003. U is equals, that is energy is represented with U or E. So we normally use U, 4774.03 joules. That's your answer. That's your answer. Let's go to the fifth one. Number 5. Find the shear stress required to slide a flat plate at a rate of 50 mm per second over a large flat surface separated from it by a film of oil of uniform thickness 0.8 mm. This thickness, somebody might want to confuse it with area, but one good thing about physics is that they normally set themselves out by giving units. You can see millimeter, so it's simply talking about length, not area. Millimeter, then and coefficient of viscosity. So let's solve it. Number 5. So to solve this question, you need to remember you are looking for shear stress represented with G. You are given velocity, which is 50 mm per second, and that means it's something like saying 50 times millimeters times 10 raised to the power minus 3 meter per second. Thickness, which is length, equals to 0.8 millimeter. But to convert it to meter, it's times 10 raised to the power minus 3 meter. Coefficient of viscosity given is 0.8. So we need to remember that from Hooke's law, Hooke's law, nothing of 1697. From Newton's law, force is directly proportional. Force of attraction between surfaces of fluid surfaces is directly proportional to the area of surface in contact and inverse of and velocity gradient. So when you now introduce equalities and introduce proportionality constant, which is eta, that is coefficient of viscosity, AV over L. This is the same as saying force equals to all over L. So if I know this force here, I can now remember that shear stress, sorry, this actually is shear modulus. This G is shear modulus. Let's not confuse it. This is stress. So shear stress will be equals to force over area. You should remember. That means shear stress, I can represent the force here with this, with everything here. So I now have coefficient of viscosity times area times velocity gradient, that is all over L, which is something divided by this area. So this is the sentence saying stress is the sentence. So reverse it 1 over E. E can take care of this E. So you now have that shear stress is just viscosity grade, coefficient of viscosity all over times velocity all over L. So what it means is that another way to define shear stress is simply product of coefficient of viscosity and velocity gradient. So when I have this now, I can now go back and substitute all those things that I was given. So coefficient of viscosity, they gave me 0.8. Viscosity, velocity itself, they gave me 50 times 10 raised to the power minus 3. The thickness, L, yeah, converting it to meter, if you remember. So it's something like 0.8 times 10 raised to the power minus 3. This can take care of this. this can take care of this. So shear stress is simply remaining 50. So it's simply 50, and stress is the same thing as or Pascal, or you say 50 Newton per meter square. So whichever one you want to use. So remember, this thing is shear stress. That's the symbol for stress. So that means I have that. So let's go to number 6. Number 6. I'm trying to kill one bird with kill two birds with one stone, doing everything together. So number 6, they said a telephone wire 1225.0 long and 1 meter in radius is stretched to. So that stretched to means it is extended to. That is from 125 to 125.2. That means the extension there is actually 0.2. That English there, maybe they put it to confuse students, but it is actually not confusing. The English is very one kind, because if you are doing this and you say stretch, there is somebody that might want to think maybe the extension there is just from 125, they now did another stretching of 125. It's just you now thinking that since it's already in 125 stretched to, it means it moved from 125 to. So sometimes they think they are confusing people, but they're actually speaking the wrong English. I believe there can be a better way to construct this type of question. But in any case, we know it. Then uh so they say when a force of 800 Newton is applied, calculate the Young modulus of the material. So let's write out the things we were given. Number 6. So I have L 125 meter. I have R 1 meter. I have stretched. That means E is 0.2. Because you will now do 125.2 minus 125, which is going to give you 0.2 for the E. Now, the force is 800 Newton. Force 800 Newton. 800 Newton. So, what they're asking us to find is Young modulus. Number 6. So, what I will now do is to remember what Young modulus. First of all, remember that Young modulus deals with stress over strain. So first, what is the stress here? So you can see stress is force over area, or you say yes over area, which is the same thing as saying force over pi r square. So here they give me force to be 800. Then they give me pi r here is 1. Anything raised to power 1 raised to anything is 1. So it's the same thing as saying 800 over 3.1429 times 1. So this will simply be the same thing as saying 254.54. Then the strain E over L will be equals to E is 0.2 all over 1.2 all over 125, sorry, which is going to give you 1.6 times 10 raised to power minus 3. So the Young modulus, which is stress over strain, will actually be 254.54 all over 1.6 times 10 to the power minus 3 is something like 0.0016. If you punch it, it will give you 159. 0.087.5. And if you approximate this 1, 2, 3, 4, 5. So this is approximately, you say it can be rounded up to 1.59 or 1.6 times 10, 1, 2, 3, 4, 5 raised to power 5 times 10 raised to power 5. We went like this. It's when we go like this, we put minus. So there you have it. So it's in Pascal, or you say in Newton meter per meter square. So whichever one, this is your final answer. Let's solve number 7. I'm trying to be very fast. Okay, let me stop here. I'll solve number 7 and number 8 next. Subscribe to my channel.